In our previous video, we looked at a uniform distribution, and we're continuing our discussion about continuous distributions. So let's look at the normal distribution. A normal distribution is a continuous probability distribution. So we have our probability distribution function, our PDF, that looks like this, where it is centered around mu, which is our expected value, our mean, and we have our standard deviation, sigma, where the majority of the data is within one standard deviation of that expected value. So the distribution is bell-shaped with a single peak at the center of the distribution. A normal distribution has the mean, the median, and the mode all being equal. Remember in previous videos, we talked about how we can compare the mean and the median, and if the two are the same, then the size of the tails are the same. It's symmetric, it's centered. But if the mean was, for example, higher than the median, that meant there were some extreme values pulling the mean, and it meant it had a bigger tail. So there was a tail on the higher number end if the mean is higher. And so let's just draw this here. So normal distribution is symmetrical. We can have a skewed distribution. So in this normal distribution, it's symmetrical. Mean, median, and mode are all right here. But if you had a non-symmetrical distribution like this one here, this means there's some high numbers that are pulling the average up compared to the median and the mode. If you have a distribution that looks like this, there's a bunch of low numbers pulling the mean down. So the mean would be less than the median, and then the mode would be right here. So only with this normal distribution that is completely symmetrical do you have the mean, the median, and the mode all equal to each other. So when we look at describing our data with summary statistics, we look at the mean, median, and mode because even without drawing a graph, we can tell how symmetrical it is. And if you want to know whether or not you are close to a normal distribution, is that mean, median, and mode, are they approximately the same? Okay, so with a normal distribution, the probability density function is symmetrical, centered on that mean. The distribution is asymptotic. What we mean by asymptotic is that those tails, they never touch the x-axis. They never cross it. So that means the probabilities get closer and closer to 0%. The bigger the number, the smaller the number. So on those extremes, the probabilities get smaller and smaller. But they never get negative probabilities because probabilities have to be between 0 and 1. And they never get truly to 0. They just get more and more decimal places. They get tinier and tinier. So they're asymptotic, meaning they get closer and closer but never touch. A normal probability distribution is completely described by two parameters here. We have the mean and the standard deviation. And the standard deviation is simply telling us whether it's going to be a more squat normal distribution, whether it's going to be fat or skinny, is what that standard deviation is telling you. So there's a family of normal distributions depending on those different combinations of mu and sigma. So here, for example, we're changing sigma. And as we said, that makes your distribution more fat or skinny. So the smaller that sigma is, the more tall and skinny it's going to be. And the bigger your sigma, the more variability in your data. And so the bigger, fatter your distribution will be. If you change the mean, that's going to shift where the distribution is located because it's going to be centered on that mean. So if you make the mean bigger, it's going to shift the graph to the right. Okay. We're going to spend most of our time as we look at inferential statistics, looking at the standard normal distribution. So we're ultimately going to create a normal distribution where the average mu here is 0 and the standard deviation is 1. Okay, but we'll start first with just the probability distribution function of a normal distribution. And it's kind of this ugly formula. We're not going to make you do the math on this. Again, remembering distribution functions. I never remember distribution functions. That's because people don't do statistics by hand. You do it in Excel, you do it in Python. All this stuff is built in. You just need to know the commands and codes. So right now we're focused on what it is, and then in our later videos we'll apply it, and you'll never have to actually remember this formula. So probably distribution function looks like this. All right, why should we care? All right, why should we care about normal distribution functions? Well, we're going to use a lot of normal distribution functions. In science and nature, many probability distribution functions very closely resemble the normal distribution function. And that's because when you're dealing with large enough numbers, it starts to have a normal distribution. Even if it's the binomial distribution, right, where you toss the coin and there were two outcomes and they were discrete, if you have enough trials, it starts to look like a continuous normal distribution. So we kind of gravitate in the real world to this normal distribution because when we have big enough data, we tend to see this nice normal distribution shape. So if n is sufficiently large, then we get a normal distribution. And as I said, we're really going to focus on this standard normal distribution where the mean is 0 and our standard deviation is 1. So if we're going to standardize our distribution, then we need to be able to use what we call z-scores or z-scores. So z-scores if you're in Canada, z-scores if you're in the States. And what we're doing here is that we are converting what would have been our x's, right? This would have been x. We're going to turn this into where our mean is 0, our standard deviations equal 1. So what we're going to do is we're going to take these x's here and we're going to convert them into z's, z-scores. So to do that, we need this formula here. We take our value of x, we subtract the expected value or average, and we divide by the standard deviation. And this will convert us to a standard normal distribution that is centered around 0. So we're just making an adjustment. Essentially, you're moving your x over by taking out the average so that you're at this 0 point, and then adjusting it for how far away you are from the average so we have that standard deviation. So values for the random variable are converted from x's to z-scores. The z-scores tell us how many standard deviations our data is above or below the mean. The z-score alters the mean and standard deviation of the random variable, but not the relative location of the score, so we maintain the information. We just standardize it. We get to machine learning and creating machine learning models, classification models, cluster analysis. We will do a lot of standardization, standard normal, and that's what we're doing here is we're essentially going to be applying this approach. That allows us, then we have different variables that are in different measurement scales to kind of standardize them so that we can use them together without one size or scale dominating the model. So standard normal is used a lot, and we'll be using that in our other videos. All right, let's take a look. The weekly income of a shift foreman in the glass industry follows the normal probability distribution with a mean of 1,000, so mu equals 1,000, and our standard deviation is 100. All right, so let's find our z-scores. So remember, z is equal to x minus mu divided by sigma. So we would just take the 1,100, subtract the 1,000, divide by 100 to get our z-score. And in this case, 900 minus 1,000 divided by 100. So if we're doing this in Excel, 900 minus 1,000 divided by 100. Our z-score here is -1. Right, 1,100 minus 1,000 is 100 divided by 100, 1. Okay, 1225 minus 1,000 divided by 100. So you can see how you could standardize the numbers. It maintains the integrity of the data because you haven't changed the relationship of the numbers to each other. You're simply shifting them over so they're centered around 1,000 here, and the standard deviation, then adjusting them so that they're on a relative scale. Okay. All right, so what if we have that? What if we want to find what's the probability that the foreman will make less than 775 next week? Okay, how do we go about finding this information? Well, we can convert that into a z-score and then use a standard normal table to find this information. So let's do this. Let's take our z equals, and we'll take our 775 minus our 1,000 and divide by our 100. So our z-score here, 775 minus 1,000 divided by 100, we get a z-score of negative 2.25. So what we really want to know is what is the probability that we have a z less than negative 0.225. Okay, if you have a standard normal table, it will look something like this. They are sometimes reported differently, so be very careful if you're using a standard normal table about what it says. This one says the table represents the area to the left of the z-score. So here's our standard normal distribution. Here is where z equals 0. So when you look at z equals 0, it's telling you that all this area here is 0.5. Sometimes when you find standard normal tables, they won't do area to the left, they will do area to the center, and so then you have to add the extra. This would then say 0, and you would have to add the 50% if you wanted to go fully to the left. So be very careful about when you find your z-score table, if you're using one, how it is reporting the information. All right, so in our case, we want to find negative 2.25, and we want to know less than negative 2.25. Negative 2.25. So we want this area out here in the tail. So this type of table that says area to the left is going to be helpful for us, but we need a negative 2.25. So we go to the table and we pick the page that has got the negatives on it, negative 2.2, and we're looking for 5. So the probability that you are left of negative 2.25, which is less than 2.25, is 1.22%. So what is the probability that a foreman will make less than 775 next week? Well, that's that 1% we just looked up. What's the probability that a foreman will make more than 1225? So here we want the probability that x is greater than 1225. Okay, so we need to find our z-score. So we're going to take 1225 minus 1,000 divided by 100, which gives us 1225 minus 1,000 divided by 100 gives us 225. So we're looking at the probability that z is greater than 225, which is going to be 1 minus the probability z is less than 225. So if we go back into our standard normal table, here we have 225, 98,778. That's the probability of everything less than all this. We want to know the probability that it's greater than, so we want the rest of it. So what we would do then is do 1 minus, of course I run out of space here, 1 minus that 0.98 what was that? 7.78%, 98778. And so we get 1 minus that, 1 minus 0.98778. Of course, got to put an equal sign in front of it to get a number. And we get 0.0122. So notice that the probability that a foreman will make less than 775 next week was 1%, and the probability that the foreman will make more than 1225 was also right around that 1%. What if we want the probability that a foreman will make between 900 and 1225? So if we're looking at this on the distribution, if this is 900 and this is 1225, you're wanting this area that's in between. In order to do that, remember that our table shows everything to the left. So if we find the probability that you're less than 1225, that's everything this way. And if we find the probability that you're less than 900, that's everything to the left here. So if we take the probability that x is less than 1225 and subtract the probability that x is less than 900, we'll get this area that's in between. To do that, we got to turn these into z-scores. So let's do this. Probability that z is less than 1225 minus 1,000 divided by 100. And then we're going to subtract from that the probability that z is less than 900 minus 1,000 divided by 100. Okay, so let's find what those are. So we have the 1225 minus 1,000 divided by 100. We already have that that's probability that z is less than 2.25. And then we're going to subtract from that the probability that z is less than, well, 900 minus 1,000 is negative 100. So this is going to be negative 1. All right, so let's go to the table. And we have 2.25 is that 0.98778. The probability that we are less than negative 1 is 15866. So let's take this number and subtract 0.15866. So if we do that, we get equals 0.98778 minus 0.15866, and we get 83%. So the probability that the foreman pay will be between 900 and 1225 is 80. What do we say it was? 80. I can't remember. 83%. Can't talk and remember things at the same time. It's kind of a problem. All right. So we just did all that by hand with a standard normal table. That's a lot of calculations by hand. Too much work. Let's do it in Excel and have Excel do all of it for us. Okay, so let's pull up Excel. Somewhere is Excel. All right, come on. Excel. All right, and I'm going to find an empty spot, and I'm going to pull it so we can still see our questions. Okay, so what if I want to do all this calculation, this first calculation, wherever I put it, this first calculation here? What if I want to do that all in Excel? Well, I can have Excel do both the z-score and the lookup all in one action. So what we're going to do is we want to go to normal distribution, norm.dst, and then notice it asks for x. So in this case, that's 775. And then I want it to find the z-score. So I'm going to give it a mean of 1,000, a standard deviation of 100. Now, the kicker here is that you need to deal with it the same way you deal with the standard normal table, which is we want to get all the information to the left. So the last piece here says cumulative, do true, and it will give you the probability of less than 775, which for this particular question is great because that's exactly what we want. So notice here, the probability that a foreman will make less than 775 next week is about 1%, just like we found. What if I want to do a question like this second one here, which is what's the probability that a foreman will make more than 1225? So I'm going to do normal distribution, norm.dist. I'm going to give it the number 1225. I'm going to give it the mean of 1,000, the standard deviation of 100, and where cumulative, write true. It is going to give me the probability that you're less than 1225. I want to know the probability a foreman will make more than 1225, so I'm going to do 1 minus that number, and I get the 1% we found when we did it by hand. What about the probability that a foreman will make between 900 and 1225? So to do this, we're going to do normal distribution equals norm.dist, and we're going to find the 1225, where the mean is 1,000, the standard deviation's 100, and cumulative equals true. And then type it in correctly. And then we're going to do norm dist, and we're going to do 900, mean 1,000, standard deviation 100, cumulative equals true. So here we want the difference in between. So what I find helpful is I always draw my little normal distribution chart. I always draw my little graph here and say, what part do I really want? Here I want between 900 and 1225, which is in the middle there. And you can't see that because my face is right on top of it. There we go. Run out of places to write things. So when you are doing this with the standard normal table, or when you're doing this in Excel, you should live in a world where you find the z-score and you go, whatever that z is, you're going to the left. Your area to the left is what you are finding. Area. You can't even see that anyway. My head is on top of it. Find a new spot to write. How about here? Here. Whatever that z is, you're finding to the left. So this normal table, check it. Make sure it's to the left, whichever one you're using. Or if you're using Excel, when you do cumulative equals true, it's going to go to the left, which means you then need to either be finding less than, or do 1 minus to find greater than, or subtract the 2 if you're trying to find the middle. Okay, so you'll need to be able to do that adjustment in order to find those probabilities.